Hello friends, today I'm going to discuss about the rotation of matrix. So let's first discuss about the classical mechanics case. So if a system is rotated about the z-axis with an angle theta, then the rotation matrix about the z-axis can be written like this: cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So this is the rotation matrix about the z-axis. Similarly, the rotation matrix about the y-axis can be written like this: cos theta 0 sin theta 0 1 0 minus sin theta 0 and cos theta. In the same way, if we talk about the rotation matrix about the x-axis, the matrix can be written like this: 1 0 0 0 cos theta sin theta 0 minus sin theta and cos theta. So these are the cases for the classical mechanics. So friends, let's now come to the quantum mechanics case. In quantum mechanics, the rotation matrix R theta can be written like this: e raised to the power minus iota theta sigma over 2, where sigma is the Pauli matrices. So we are having three Pauli matrices which are given by sigma x, sigma y and sigma z. So if we want to calculate the rotation matrix about the x-axis, then we'll just replace the sigma with sigma x, right? So using the property of the Pauli matrices, we can write like this: cos theta multiplied by the identity matrix minus iota sin theta over 2 multiplied by the sigma x. Then we substitute the value of the identity matrix here and the first Pauli matrix here: 0 1 1 0. So after simplification, here we just multiplied cos theta with the elements of this matrix. So this will give us cos theta 0 0 cos theta. So similarly, if we multiplied this with this matrix, this will give us 0 iota sin theta over 2 and iota sin theta over 2 and 0. So after simplification, the Rx can be written within this 2 cross 2 matrix like this: cos theta over 2 minus iota sin theta over 2, then minus iota sin theta over 2 and cos theta over 2. Similarly, if we are going to calculate the rotation matrix about the y-axis, we will just write in the similar way, just replacing the sigma x with sigma y. So this is very simple. So after simplification, we can write this matrix like this, okay? So the final rotation matrix about the y-axis can be written like this: cos theta over 2 minus sin theta over 2, sin theta over 2 and cos theta over 2. So then coming to the rotation matrix about the z-axis, which can be written like this, okay? We'll just replace the sigma with sigma z. So after simplification, the final rotation matrix can be written like this, okay? These are the elements of the rotation matrix about the z-axis. So now let's discuss about the problem of previous year NET exam, which has been asked in 2018 December. Okay, the question is: a system of spin-half particles is preferred to be in the eigenstate of sigma z with eigenvalues +1. The system is then rotated by an angle of 60 degrees about the x-axis. So this is important. It is rotated about the x-axis. So after the rotation, the fraction of particles that will be measured in the eigenstate of sigma z with the eigenvalue of +1. So these are the information has been given. So the options are like this. Okay. Now let's solve this problem. So the main information has been given like this. The particle is spin half. the eigenstate is sigma z, eigenvalue is positive 1, then the system is rotated about the x-axis with an angle 60 degree. So we have to find the fraction of particles, I mean the probability that will be measured in the eigenstate of sigma z with eigenvalue positive 1. Okay, so let's proceed step by step. Let's first calculate the eigenstate of sigma z. So to estimate or to calculate the eigenstate of sigma z, we must have to find the eigenvalues. So eigenvalues of sigma z can be calculated from these characteristic equations, which can be found as positive 1 and negative 1. So according to the equation, we have to find the eigenstate with respect to the eigenvalue positive 1. Okay, so now let's proceed. The eigenvector can be calculated like this for the eigenvalue positive 1 here. So we'll put here positive 1. The eigenvector x1 can be written with the elements like x1, x2. This is the general procedure how to find the eigenvector corresponding to an eigenvalue for a particular matrix sigma z. Okay, so after simplifications, we can see that from this second row of these two matrices, by comparing, we can calculate that the x2 becomes 0. So the eigenvector corresponding to the eigenvalue positive 1 can be found like x1, the second element is 0. Okay, so to normalize this eigenvector, we just take the x1 dagger, x1 is equal to 1. So then the matrix, the column matrix of x1 will become the row matrix, which then multiplied with the column matrix itself. So in this normalization case, we just generally consider it as a probability, and we take only the positive value, not the negative value. So it is an important point. Okay, so now we are having the eigenvector, so which is given by 1, 0. So the rotation matrix along the x-axis can be written like this: Rx theta. Okay, this. So this rotation matrix we have already discussed. The transformation matrix can be written just by multiplying the rotation matrix with the eigenvector of the sigma z that we have already estimated it. Okay, so now we'll just put the value of the theta by 60 degree. So the rotation matrix now will become like this. So then we will multiply it with the eigenstate of the sigma z. So this will give us root over 3 over 2 and minus iota over 2. So this is the transformation matrix. Okay, so now let's proceed how to find the probability corresponding to the eigenvalue. So for spin half particles, Hz matrix, which is associated with the sigma z, can be written as psi is equal to C1 1 0 and C2 0 1. So by comparing the equation 2, this transformation matrix, with this general formula of the psi for spin half particles, so the value of the C can be written as root over 3 over 2 multiplied by the matrix 0 1 0. Similarly, the value of the C, just comparing with this transformation matrix, we can write the value of C as minus iota over 2. So this wave function, the first element is for the eigenvalue positive 1, and this second value is the eigenvalue for negative 1. Since according to the question, we have to find the probabilities or the fraction of particles with respect to the eigenvalue, so we must have to find the probability corresponding to the past eigenstate of this function psi. So this can be simply given by mod of C1 whole square. So the value of the C1 is root over 3 over 2. So this is given by 3 over 4. Therefore, the option D is the correct answer. Thank you.